Right, chemistry. The science of matter, reactions, energy, and let's be honest, some of the most satisfying moments of intellectual satisfaction you'll have in school. Welcome and welcome back to IB Tips and Chips. This video is your orientation guide to IB chemistry. By the end, you'll know exactly what the syllabus covers, how the courses are assessed, what the internal assessment requires, and crucially, what actually works when you're studying for it. Whether you're doing SL or HL, this video is for you. And where those two courses differ significantly, I'll flag it clearly. Let's get into it. First, what is IB Chemistry? IB Chemistry sits in Group 4 of the diploma program, the Sciences Group. It's fundamentally about understanding matter, what it's made of, how it behaves, why it reacts, and what drives those reactions. The new syllabus, first assessed in 2025, is built around two organizing ideas: structure, what matter is and how it's built, and reactivity, why and how matter changes. Everything in the course connects back to these two core concepts. The big idea is that structure determines reactivity, which in turn transforms structure. Once that idea clicks, the whole course starts to make a lot more sense as a connected whole rather than as a collection of isolated topics. The course trains you to think like a chemist, to build models, apply mathematics, interpret data, and reason from evidence. It also involves regular practical work in the lab, which isn't just extra, it's built into the core of how we learn. The main differences between standard level and higher level are the hours total. In standard level, you have 150 hours in total, whereas in higher level, you have 140 hours. This means in higher level, there is a lot more content, including entropy, Gibbs free energy, and things like that. Now, the syllabus. The 2025 chemistry syllabus has a new structure that's genuinely elegant. Instead of a long list of disconnected topics, everything is organized under two big concepts: structure and reactivity. Each divided into three major sections. Let me walk through them. First, structure. Structure 1 is called Models and of the Particulate Nature of Matter. This is your foundation: elements, compounds, mixtures, kinetic molecular theory, atomic structure, isotopes, mass spectra, electron configurations, the mole, ideal gases. The stuff you've probably started touching in previous science courses, but now at a level of precision and depth you haven't seen before. Structure 2 is models of bonding and structure: ionic bonds, covalent bonds, metallic bonding. Lewis structures: VSE, PR, and molecular geometry. Intermolecular forces: London dispersion forces, dipole-dipole, hydrogen bonding. Polymers, alloys, and advanced materials. HL students add resonance structures, hybridization, sigma and pi bonds, and expanded octets. Structure 3 is the classification of matter. The period table, trends, periodicity, transition metals, and organic chemistry, functional groups, IUPAC nomenclature, homologous series, isomerism. HL adds stereoisomerism, chiral centers, and spectroscopy, including mass spectrometry, IR, and MNR. Now, reactivity. Reactivity 1 is what drives chemical reactions: thermochemistry, enthalpy, Hess's law, energy cycles, fossil fuels, biofuels, fuel cells. HL adds entropy and gives free energy. Reactivity 2 is how much, how fast, and how far. Stoichiometry and mole calculations, reaction rates, collision theory, activation energy, catalyst, Maxwell-Boltzmann distributions, and equilibrium. Higher level adds rate equations, the Arrhenius equation, reaction order, and detailed equilibrium calculations. And reactivity 3 is what are the mechanisms of chemical change, the big one: acids and bases, redox reactions, electrochemistry, radical reactions, and nucleophilic or electrophilic reactions. HL adds SN1 and SN2 mechanisms, electrophilic addition and substitution, Lewis acid-base theory, and electrochemical cell potentials. Now, as we can see here, SL has way less hours than HL, and the main difference is in mechanisms, which SL only touch on slightly, whereas HL develop it a lot further. Now, how to actually study this subject. Chemistry rewards a very particular kind of studying. Let me give you the honest version, the advice that actually works, rather than generic study tips. First, what works for all of the levels? First, build your understanding before you memorize anything. Chemistry at this level is about understanding why things happen. If you understand the reasoning, the facts follow naturally. Do practice questions from day one. Don't wait until you've finished a topic. Attempt questions as you go. It's how you find out what you actually understand versus what you actually think you understand. Keep your equation and constant notes organized. Summaries of key equations, reaction types, and their conditions save enormous time at revision. Use the data booklet constantly during practice. Train yourself to reach for it exactly as you would in the exam. Don't neglect the mathematical side. Mole calculations, enthalpy calculations, equilibrium expressions, pH, these require practice and precision. Work through lots of calculation problems. And lastly, understand the command terms. State, describe, explain, deduce, discuss. These words tell you exactly how much depth to give. State needs only one or two words. Explain needs reasoning. This distinction costs students marks every single year. Now, specific advice. First for SL. Your course is already demanding. Don't underestimate it. SL chemistry is not a soft option. Focus on being fluent in the core reactions: combustion, neutralization, redox, and the main organic reactions. These come up constantly. In calculations, always show you're working. Always include units. Even if your final answer is wrong, you can earn method marks. The most common SL mistake is rushing through topics without securing the fundamentals. A shaky understanding of moles and stoichiometry will cause you throughout the entire course. Now for specific advice for HL students, the HL extensions are where the real conceptual depth kicks in. Entropy and Gibbs free energy, the Arrhenius equation, rate equations, buffer calculations, NMR and SN1 or SN2 mechanisms. These are not just more content, they require genuinely deeper thinking. Also, HL exams are longer and require faster application. Build your speed through timed practice under exam conditions. Make strong connections across the syllabus. The linking questions throughout the guide signal where the IB expects you to see connections between bonding and reactivity, between structure and physical properties, between thermodynamics and equilibrium. Examiners require integrated thinking. The most common HL mistake is memorizing mechanisms without understanding the electron movement behind them. Learn why electrons move the way they do, and you can reason through any mechanism even if you've not seen it before. Now, the external assessment first. External assessment, the final exams, makes up 80% of your chemistry grade. You said two papers, paper 1 and paper 2. Let me break each of them down for both SL and HL. Paper 1 is split into two booklets, 1A and 1B, sat back to back without interruption. Paper 1A is multiple choice, 30 questions for SL, 40 for HL. No marks deducted for wrong answers, so you should always attempt to write down an answer for every single question. These test knowledge and application, they're not just recall, as many require you to reason from data or apply a concept in a new context. Paper 1B is database, 25 marks for SL, 35 for HL. You're giving experimental data, graphs, or spectra, and asked to interpret and analyze them. This is where your practical skills and understanding of uncertainties are tested in an exam context. Now, paper 2 is short answer and extended response. This is where your ability to communicate chemistry clearly and precisely really matters. You'll encounter a mix of question types: structured questions requiring precise answers, database questions, and extended response questions worth several marks that require you to construct a coherent explanation or argument. Now, on the other hand, the internal assessment. The internal assessment is worth 20% of your final chemistry grade. It's the same requirement for SL and HL students. You complete one piece of work, the scientific investigation, and submit it as a written report of up to 30,000 words. This is an open-ended independent investigation. You choose your own research question, design a methodology to investigate it, collect and process data, draw conclusions, and evaluate your work. It's genuinely one of the best parts of the IB because it's yours. You get to investigate something you're actually curious about. First, you have to formulate your own research question with a dependent and independent variable. You also have to design and carry out methodology, lab experiments, fieldwork, database analysis, and modeling. Collecting and process quantitative data, supported by qualitative observations. Write a full scientific investigation report, maximum 3,000 words, with tables, graphs, equations, and references, which do not count towards the limit. And this is your own individual work. Even in collaborative data collection, the report must be entirely your own. The assessment criteria are A, B, C, and D, and add up for a total of 24 marks. A good IA will have in the first one a 5 or a 6 out of 6, which means that the research question has specific context, including background theory, variables are named, methodology is reproducible, and shows consideration of safety and control variables. For criterion B, data analysis, data is recorded cleanly and precisely, uncertainties are propagated correctly, processing is relevant and accurate, graphs are properly labeled with units and error bars. For criterion C, conclusion directly addresses the research question, is fully consistent with the processed data, including uncertainties, and compares quantitatively to published or accepted scientific values with proper citations. And the last one, evaluation, identifies specific weaknesses, not generic ones like human error, explains the relative impact of each on the conclusion, and proposes realistic specific improvements. Alright, let me be honest with you for a moment, student to student. IB chemistry is genuinely challenging. There is a lot of content, and the level of precision required in calculations, in language, and experimental thinking is higher than most students expect. That's the honest truth. But here's what is also true. Students who engage with it properly, who actually do the practice questions, who work through confusion rather than avoiding it, and actually ask for help early, those students consistently do better than they expect. Now, good luck, and now go do some chemistry.